trigonometric integrals. In this section, we're going to take a look at some integrals that involve powers of trigonometric functions. We're going to see a couple of strategies that we can use in evaluating these types of integrals. We'll start with an example of what to look for in this section. Alright, so let's consider the integral of sine cube theta by cosine fourth theta d theta. We might say, well, maybe we should try and use parts, since we've just learned that technique. But if you think about the by parts process, we would have to, in a sense, integrate one of these factors, and we don't have a technique for integrating either of them. So instead, what we're going to do is we're going to use, well, I'm going to show you the idea here, and we're going to talk about why I chose to do what I did. So here's what I'm going to do. I'm going to sort of split up this sine cube theta. I'm going to rewrite the integral as sine square theta times cosine fourth theta times sine theta d theta. I say, well, why did I do that? Well, now I'm going to use a little bit of trickery, I suppose. Not really trickery, but look what happens. Suppose I let u equal cosine theta. Well, then du is negative sine theta d theta. And so notice, well, I've got the sine theta d theta, so I would need a negative in here, and I need to bring a negative on the outside. But now what about that sine square theta? Well, I remember from trigonometry that sine square theta plus cosine square theta is 1, and so I can replace that sine square theta with 1 minus cosine square theta. So now the integral becomes negative integral. Now sine square theta, I'm going to replace that with 1 minus cosine square theta. And then I still have the cosine fourth theta. And I have the negative sine theta d theta. And now everything is nice. With that substitution, letting u equal cosine fourth theta, then this integral becomes simply negative integral 1 minus u square times u to the fourth du. And so that's negative integral of u to the fourth minus u to the sixth du. So that's negative 1/5 u to the fifth minus 1/7 u to the seventh plus a constant. And so then substituting back in terms of the original variable, the integral is negative 1/5 cosine fifth theta minus plus 1/7 cosine seventh theta plus a constant. And of course, we could check our work through multiplying, differentiating, and we'd have to use some trig identities again to get it back into the original form. But this is the idea. We're gonna carefully choose our u and use some trigonometric identity in evaluating these integrals. Alright, so here's a strategy for evaluating if we have a product of sines and cosines. If we have sine mx times cosine nx dx. If the power on the cosine is odd, we're going to save a cosine factor. We're going to get rid of all of the others using the fact that cosine square of x is 1 minus sine square of x. So the idea is, if the power on cosine is odd, keep a cosine, get everything else in terms of sine. Similarly, if the power of sine is odd, keep one of the sines and get rid of all of the other signs by turning them into cosines. Now, if the powers of both sine and cosine are even, then we have to use a little bit of a different technique. We use the following identities to get this in terms of just the cosine function. So if everything's even, we use the fact that sine square x can be written as 1/2 of 1 minus cosine 2x, and cosine square x is the same as 1/2 of 1 plus cosine 2x. Right, and sometimes we also might need to use the identity that sine x cosine x is equal to 1/2 sine 2x. So they don't always fall into a nice pattern, but we can often use these ideas to get us through. Alright, so let's consider another example. Here we have the integral of sine 4th x times cosine cube x dx. Alright, so what I'm going to do here is I notice that I have an odd power on the cosine. I'm going to keep one of the cosines. So in a sense, what I'm going to do is I'm going to rewrite this as sine 4th x times cosine square x times cosine x dx. I need to keep that cosine x dx. And I'm going to make the substitution that u equals sine x. And if u is sine x, then du is cosine x dx. So that's going to take care of this sine 4th x, that's u to the 4th, and the cosine x dx, that's du. And so now all I need to do is get rid of this cosine square x. So I'm going to use the fact that cosine square x is 1 minus sine square x, which with my substitution, that's 1 minus u squared. And so then the integral becomes the integral of u to the 4th times 1 minus u squared du. So that's the integral of u to the 4th minus u to the 6th du. And so that's 1/5 u to the 5th minus 1/7 u to the 7th plus a constant. And so substituting back, that's 1/5 sine 5th x minus 1/7 sine 7th x plus a constant. All right, so there is another example. This one's a fairly straightforward example of this technique. All right, what if we had to evaluate the integral cosine 4th t dt? All right, so this is an example of when we don't have any odd powers on the sines or cosines. And so what we do with this is we use that reduction formula that we talked about. So we've seen, we saw earlier that I can write cosine square x as 1/2 of 1 plus cosine of 2x. So then the integral of cosine 4th t dt, well, that's the same as the integral of cosine square t, that whole thing squared, dt. And so then the integral becomes the integral of 1/2 of 1 plus cosine 2t squared dt. Alright, so now simplifying, this becomes, well, 1/2 squared is 1/4, and then 1 plus cosine 2t squared, that would be 1 plus 2 cosine 2t plus cosine squared 2t dt. Alright, distributing and separating this out a little bit. 1/4 times 1 is 1/4, so this becomes the integral of 1/4 dt plus 1/4 times 2, that would be 1/2 cosine 2t dt plus, and I'm going to 1/4 times 1, that would be 1/4 cosine square 2t dt. All right, now if we look at each of these, that's fairly simple. Right? The integral of 1/4 dt, that's an easy integral. 1/2 cosine 2t dt, this is not too bad. This is a u sub. We just need to let u equal 2t. And we can evaluate this integral. This last integral, 1/4 cosine squared of 2t dt, since it has that cosine square in again, I'm going to use that same reduction idea. All right, so what I have here is then this becomes plus, let's see, I'd have 1, I can bring the 1/4 outside, and now cosine square of 2t, that would be 1/2 of 1 plus cosine of 2 times 2t. All right, so let's see, that would be 1/8 times the integral of 1 plus cosine 4t dt. And now again I can use a u sub on, right here I would need a u sub, let u equal 4t. All right, so on this first integral, if you, let's see, the integral of 1/4 dt, that's 1/4 t. On the second integral, if I let u equal 2t, then du is equal to 2 dt, so I would need a 2, and I would need another 1/2. And so this would become then the integral of, this would become 1/4 times the integral of cosine u du, and so that would be 1/4 sine u. So this would be plus 1/4 sine 2t. All right, now in purple, I'd have a plus 1/8 integral of 1/8 dt, and so that's going to be a plus 1/8 t. And then on the last term, since that's a plus 1/8 integral cosine 4t dt, letting u equal 4t, then du is 4 dt, so I need a times 4 on the inside, and a times 1/4 on the outside, and so then this is going to be plus 1/32 sine of 4t plus a constant. Now we do have a couple of like terms here. We have a 1/4 t and a 1/8 t. 1/4 plus 1/8 is 3/8. So then I can write this as 3/8 t plus 1/4 sine 2t plus 1/32 sine 4t plus a constant. So that's how we can use the reduction idea to evaluate integrals where we just have even powers of sines and cosines. I wanted to show one more example with sines and cosines that was a little bit different than the other ones. Let's suppose we wanted to evaluate the integral of sine square x by cosine 5th x dx. All right, so I see the odd power on cosine, so what I'm going to think here is keep a cosine. So I'm going to write this as the integral of sine square x cosine 4th x cosine x dx. Now I'm going to let u equal sine x, so then du is cosine x dx. I've got my du, but now I have this cosine 4th x. Well, cosine fourth x is cosine square x square, and cosine square x is 1 minus sine square x square. So then after substitutions, that becomes the integral of u squared times 1 minus u square square du. And so now we have the integral in a completely algebraic form. And we have to be careful here. That 1 minus u square square, that's where I would expect an error, possibly. So then this becomes the integral of u squared times 1 minus 2u squared plus u to the fourth du. And so then that's u squared minus 2u to the fourth plus u to the sixth du. And so now integrating, just using the general power rule for integrals here, we'd have a 1/3 u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh plus a constant from the integration. And now substituting back in terms of x, 1/3 sine cube x minus 2/5 sine fifth x plus 1/7 sine seventh x plus a constant. Now, if we have integrals that involve powers of tangents and secants, then we can use some similar ideas, but things are a little different. If the power of the secant is even, we save a factor of secant square x and use the substitution that u equals tangent x. And we're going to use the Pythagorean identity, that's secant square x is equal to 1 plus tangent square x. If the power of tangent is odd, we save a factor of secant x times tangent x, noticing that that's the derivative of the secant x. And again, we use that same identity just in a different form. Tangent square x is equal to secant square x minus 1. Now, if we have other situations where, the secant's not even and the tangent's not odd, it can get a little tricky. We have to use some more ingenuity. We might have to use a combination of different techniques. And we also want to keep in mind some established formulas. We figured out these back in the previous chapter, or previous topics. We learned that the integral of tangent x, plain old tangent, is natural log of the secant x, of the absolute value of the secant x, and we also determined how to evaluate the integral of the secant x as the natural log of the absolute value of secant x plus tangent x. Alright, so let's see a couple of examples of how to deal with this. Alright, so here's our first example with tangents and secants. So here I'm asked to evaluate the integral of tangent cube theta by secant cube theta d theta. Alright, so here's what I notice. I've got this product of tangents and secants, and I notice that the power on tangent is odd. So, since that power on tangent is odd, I'm going to keep a tangent theta secant theta, or other secant theta tangent theta. All right, so I'm going to rewrite this then as the integral. If I'm going to keep a tangent theta secant theta, I can write this as tangent square theta secant square theta times secant theta tangent theta d theta. Alright, and so remember that that is the derivative of secant theta. So that tells me the substitution. I'm going to let u equal secant theta. Then du is secant theta tangent theta d theta. Alright, now that takes care of the secant square theta, and that takes care of the secant theta tangent theta d theta. So now, what about that tangent square theta? Well, remember that tangent square theta, from our identities, tangent square theta is equal to secant square theta minus 1. So then this integral becomes tangent square theta is secant square theta minus 1. That's u square minus 1. Secant square theta is u square, and secant theta tangent theta d theta is du. And so again, this is entirely algebraic now. And so this becomes the integral of u to the fourth minus u squared du. So that's 1/5 u to the fifth minus 1/3 u cubed plus the constant. And now substituting back in terms of the original variable, I'd have 1/5 secant fifth theta minus 1/3 secant cube theta plus a constant. All right, we're asked to evaluate the integral of tangent square theta secant fourth theta d theta. This would be a good one to try on your own. So now would be a great time to pause. I see that we have an even power on the secant factor. So, since the power on the secant is even, I'm going to keep a secant square theta. So let me rewrite this integral as the integral of tangent square theta times a secant square theta, and then times secant square theta d theta. And so since I'm going to keep this secant square theta d theta, I want that to be my du, so the substitution is u equals tangent theta. If u is tangent theta, then du is secant square theta d theta. And so that takes care of this tangent square theta, that would be u square, and secant square theta d theta, that's the du. The secant square theta, remember then that secant square theta is the same as 1 plus tangent square theta, again from the Pythagorean identities. So then the integral becomes the integral of u square times 1 plus u square times du, which is the integral of u to the second, or u square plus u to the fourth du. And so then that would be 1/3 u cubed plus 1/5 u to the fifth plus a constant. Substituting back, we'd have 1/3 tangent cube theta plus 1/5 tangent fifth theta plus a constant. Evaluate the integral of tangent square x times secant x dx. All right, so if we analyze this integrand and we look at the powers, we have an even power on tangent. Well, that's not good. We want an odd power on tangent. We have an odd power on secant. Well, that's not good. We want an even power on secant. So this doesn't fit into either of those nice situations. So here we have to use a little bit of ingenuity. We're going to have to mix together a couple of techniques. All right, so what I'm going to do first here is I'm going to rewrite this integral as the integral of tangent x times secant x tangent x dx. And so when I look at it like this, I think there's sort of a natural, it looks like I could use integration by parts here. And that's what I'm going to do. I'm going to use integration by parts with u equal to tangent x and the dv being secant x tangent x dx. So if u is tangent x, then du is secant square x dx. And if dv is secant x tangent x dx, then v would be secant x. All right, and so then by parts, this integral becomes, all right, so this was the original integral. All right, so my integral becomes uv, that would be tangent x secant x, minus the integral of v du. That would be the integral of secant x times secant square x dx. All right, well now, this doesn't look much better because now I've got a secant cube x. All right, if we were to think about that, I've got a secant cube x. So, all right, what if I now use an identity? I know that secant square x is equal to 1 plus tangent square x. And so then this becomes, the integral is equal to still tangent x secant x minus the integral of secant x plus secant x tangent square x dx. Now wait a second, let me break up that integral. And so the integral becomes tangent x secant x minus the integral of secant x dx minus the integral of tangent square x secant x dx. Now look at this for a moment. This is known, but this is unknown, and that was the original integral, wasn't it? That is I. So notice what I've got here. I've got this I, this integral, this original integral on both sides of the equation. So let me rewrite this. Let's see. The integral is then tangent x secant x. Now, a known formula, the integral of secant x, and I just mentioned this towards the beginning of this, on that slide, sort of in the middle of the section. This is the natural log of the absolute value of secant x plus tangent x minus the integral. So let me add this integral to both sides. And so now I have twice the integral is equal to tangent x secant x minus the natural log of the absolute value of secant x plus tangent x. And I suppose there should be an integral from, I should have had an integral, a constant from integration in here somewhere. So let me just put a plus c on here. So there's a plus c. And now to solve for the integral, all I have to do is multiply both sides by 1/2. And so then the integral I would be 1/2 of tangent x secant x minus the natural log of the absolute value of secant x plus tangent x. And I can close off the brackets here because if I multiply a constant by 1/2, I still get a constant. All right, so that one's a little tricky, and this happens sometimes when especially when we're dealing with exponentials and trigonometric functions. We sometimes have to use this sort of trick, and that we end up with the integral, the original integrand on both sides of this equation, and then we have to solve for the integral. All right, that completes the presentation for this section.